All right, welcome to lab. We'll get started in just a little bit here. Again, we're going to go over that example that hopefully you've been working on during this little break in between lecture and so forth. And hopefully everything is stabilized in terms of our meeting. So again, we'll start in just a minute or so, and we're going to go through this example to make sure everybody's on the same page in terms of titrations. And then afterwards, we will talk about the next experiment, which is buffers. And we'll talk about some aspects of that as well. So again, if you're just coming in, we're going to go over this example here, the different parts of it, make sure everybody understands calculation correctly. And then obviously we'll continue on to talking about buffers experiment, which is not currently posted up there on Canvas, but as soon as we're done here, I will post it up there so you can see it and you can start working through that one as well. We're just going to give everybody a minute or two here, just kind of come in, and then we'll get started. All right, so why don't we get started and kind of go through this example. So this is a titration problem, and this is typically how titration problems are basically sort of given to you. They don't usually give you the graph per se, but they'll just sort of give you two in words. So we're doing a titration with 100 milliliters of 0.1 molar nitrous acid, and we're titrating it with 0.1 molar sodium hydroxide. And we want to find the pH at some different points along the titration. So initially, before we add anything, after we add 80 milliliters of the sodium hydroxide, we also want to find the pH at the equivalence point. And then lastly, we want to find what the pH is after we've added 105 milliliters of base. We have a Ka value for HNO2 given to us of 4.5 times 10 to the minus 4. So automatically, just from the problem, it should give you some hints about what's going on. We see a Ka value down there, which obviously would imply that HNO2 is a weak acid. We also know NaOH is a strong base. So this is our titration of a weak acid with a strong base. So again, we want to make sure we sort of understand those things. Again, it's going to help you understand sort of what's going on at each step along the way, or what should be going on at each step along the way. So this again is a weak acid, strong base titration. Up in the burette is our sodium hydroxide, and down in the beaker to which we're adding is where our acid would be. So again, here we're adding the base to the acid, and we basically want to go through it. So we're going to start with the excuse me, the first part there, which is part A, and that's before we add any sodium hydroxide to it. So obviously in part A, the only thing that we have for part A is that weak acid that's in there. So we have just a weak acid. And that means that this type of problem here would be just a basic weak acid problem, which means it's basically a Ka problem. Also, in this case, since we have not added any sodium hydroxide to it, we don't have to worry about doing anything in moles. We could just do it in molarity. So let's take a look at this. So for part A, initially, no sodium hydroxide added. Again, the only thing we would have in this case is our weak acid, which is nitrous acid. It will dissociate. And as we talked about earlier today, you do need to do an ice table. And your ice table should look something like this. We are going to use our initial concentration of the nitrous acid, which is 0.1 molar. We also, while we're here, are going to need that Ka value of 4.5 to the minus 4. And I believe that was right? So minus 4. So initially here in this table, we have 0.1 molar, 0 for this guy, 0 for this guy. We're going to do a change, which is going to be minus x minus plus x plus x. We're going to come to equilibrium, which is 0.1 minus x, x, and x. This is going to go into our Ka expression. So our Ka, right, our products over our reactants, that's going to give us x squared on top. It's going to give us 0.1 minus x on the bottom, and that's going to equal 4.5 times 10 to the minus 4. You can assume that x is equal to 0 here. And if you do, that gives you x squared over 0.1 is equal to 4.5 times 10 to the minus 4. That will give you an x value if you solve for it. Of something like 6.7 times 10 to the minus 3. We would want to check it by dividing by 0.1 and times it by 100. And in this particular case, when we do that, we end up with 6.7%. And that, again, is above our sort of cutoff for our 5% rule that we use. So you do want to make sure that you still check it. And as you can see here, technically in this case, it did not pass that rule, which means we do need to come back up here and solve it a different way. So we need to use our quadratic. So taking the bottom up there and multiplying it to the other side. So we're going to multiply this entire thing to the other side. That is going to give us 4.5 times 10 to the minus 5 minus 4.5 times 10 to the minus 4x, bringing everybody over to one side. This again would go into our quadratic equation. So and if you kind of solve all that there, you will get an x value of 0.00649, we'll call it, or an x value of minus 0.00694. Obviously, in this case, we're interested in our H plus, which is equal to x, so we cannot have our negative number. That means that in this case, the H plus concentration equals x, which would equal 0.00649. putting that into our pH minus the log 0.00649 will get you an opening pH here of our titration of 2.19. Any questions on that opening calculation? Again, it's just a basic sort of Ka problem. A good reminder as well to the right-hand side there that you should check your answer. I know in this particular case, if you did the assumption, you get like a pH of 2.17. Technically, it's wrong, right? So because it is a little bit too high of a percentage. So it won't always obviously be very close to each other. But in this case, you do get sort of an answer that's very close to each other. Even with rounding, it may be very close. But the correct way to do it based on what we were talking about and sort of how we learned it, again, is you would have to go through the quadratic here. Any questions on any of those steps there for part A of the titration? So again, here we have just a weak acid. We haven't added any base to it. So we don't have to worry about moles. We can do everything in molarity. And again, it's just a weak acid sort of problem. Any questions on that part? Okay, so let us go look at part B. In part B, we're adding 80 milliliters of our base. So let's take a look at that one here. All right, so in part B, we're actually starting the titration. We're going to add 80 milliliters of our 0.1 molar sodium hydroxide to our 100 milliliters of our 0.1 molar nitrous acid. Again, same Ka value that we used previously, which is our 4.5 to the minus 4. So obviously in this case, we have started the titration. So we are going to have a reaction, obviously, between our acid and our base. And we will get some water and we will get some sodium nitrite. Since we did do a addition here of volume, we do want to make sure we do this ice table in moles, right? So we do need to figure out the moles of each of those guys. So again, a reminder for our sodium hydroxide. Oops, if I don't hit the button there. Our sodium hydroxide moles. We would take our volume, which is in this case 0.08 liters. We would times it by our molarity, which is 0.1 molar, 0.1 moles per liter. Liters are going to cancel. And for our sodium hydroxide, 0.08 times 0.1 gives us 0.008 moles. And again, that would be our initial. And we do want to do it in moles here. We'll do the same thing for our nitrous acid. So that's going to be 0.1, which is the 100 milliliters, times 0.1, which is the molarity. And we get 0.01 moles for this guy. Again, doing the same calculations we did for our sodium hydroxide. It would be 0 at this point for our sodium nitrite. Again, here we're adding the sodium hydroxide. We're starting with our nitrous acid. And if you're not sure where we are in terms of the titration curve, we have less moles of what we're adding to the moles we're starting with. So that should tell you you're actually before the equivalence point. So it definitely should tell you you're before the equivalence point. If you're not sure, you could use the table to figure that out. Again, if you're adding less moles than what you started with, you're before the equivalence point. If you're adding the same number of moles as what you started with, you're at the equivalence point. And if you're adding more moles than what you started with, you're past the equivalence point. So what that means is the change part here is going to be the sodium hydroxide. So we're going to take minus 0.008, minus 0.008, and plus 0.008. Here again, I'm ignoring water because it will not have an effect on the pH. So you don't have to worry about trying to use the number where you shouldn't. And if we do that, 0.002 moles, 0 here, and 0.008 moles. At this point, like we talked about, after you do the first table, it's a good idea to convert back into molarity using the total volume. So in this case, our total volume is going to be the 100 milliliters we started with. We then added 80 milliliters to it. That's a grand total of 180 milliliters, or 0.18 liters. So we'll take this, divide it by 0.18 liters. We'll take this guy, divide it by 0.18 liters. That's going to turn both of these into molarity. And we will end up with 0.0111 molar for that guy, and 0.0444 molar for this guy. Any questions so far on the ice table, how we got those numbers or anything like that? So again, if you are not sure what's going on here, you again can use the ice table to help you figure out what your next steps should pretty much be. We do have HNO2 left over. We do have NaNO2 left over. So again, hopefully you can recognize that these two guys are related to each other. That is a weak acid and its conjugate base, which again means that we are in a buffer situation at this point. This is also why, if you can recognize where you're at in this titration, even before you started the calculation, you should know in this type of titration, before the equivalence point, it should always end in a buffer. So this is, again, a good way you can check yourself as you're doing these problems. And as we talked about a number of times at this point, you have two options. You could Henderson-Hasselbalch it, or you could ice table. I'm going to Henderson-Hasselbalch it. So that's going to be pH is equal to pKa plus the log of the base over the acid. Here, the pKa value will be minus the log of the Ka. And that will get you, looks like 3.35 as our pKa value. That means our pH would equal 3.35 plus the log. Again, this guy obviously is our base, so we would want the 0.0444 on top. The nitrous acid obviously would be our acid. And if we do this and a little bit of this, we end up with 3.95 as our pH at this point in the titration. Any questions on those steps? Now, I will be honest with you, technically speaking, it's really good practice that you should always convert back to molarity after that table. But the reality is, if you are using the Henderson-Hasselbalch equation and only using the Henderson-Hasselbalch equation, you actually can leave these guys in moles and it will come out the same. So, you know, you could put the moles here and you could take these moles here, and you technically will get the same when you use this equation, because the milliliters, the liters, and the liters will cancel each other out anyways. If you're doing an ice table or anything like that, you should have it in molarity. Otherwise, you might not get the right answer. But you can still obviously do it in molarity here with the Henderson-Hasselbalch equation, and it's usually probably good practice because later on in other parts, you will need the molarity for sure. So, you know, it's probably a good idea to do it in molarity. But technically speaking, you can't go in the Henderson-Hasselbalch equation with moles up on top there and bottom. Any questions on any of that? it should also make sense as well. Our first spot before we started the titration was 2.19. We have now gone up to 3.95, which we would expect the pH to start to rise as we are adding base to it. Any questions on those two there? And again, a reminder that when you have a problem such as this, for example, where there's multiple parts, you do treat each part separately in the sense of you think about it as you started as 0, and then in this case, we added 80 milliliters. Yeah. If the next one was, say, 105 milliliters, you would think of it as starting at 0 and you added 105 milliliters and shut it off. So sometimes people, when they have problems like this, like to sort of keep adding the volumes from part A to part B to part C. Unless it's specifically said to do so, you usually can treat each of these parts as like you started at 0, and that's the total volume that you added up at that point of like the sodium hydroxide. A reminder, if you do have questions, feel free to type them. We will get to them. And now we are on part C, which is the equivalence point. And we want to know, what is the pH at the equivalence point? We'll use this one with the thinking. It's a good thought there. So we're at the equivalence point. So in this case, we're to have 100 milliliters of our 0.1 molar nitrous acid. And we're adding 0.1 molar sodium hydroxide to it. Again, same Ka value, which is 4.5 to the minus 4. So in this particular case, they really didn't tell you the volume of sodium hydroxide that you would need to use to get to the equivalence point. And there's actually a couple different ways that you could figure out the volume if you needed to. So let's talk about a couple ways you could do that. The kind of truly right way, if you will, is to take the equation, which in this case, obviously, we have our HNO2 plus our sodium hydroxide, giving us our water and our sodium nitrite. And really the right way is to sort of do a stoichiometry sort of problem. So you have 0.1 liters of HNO2 times it by the molarity of HNO2. And that gives us 0.01 moles of HNO2. We're not interested in HNO2. We want to know about sodium hydroxide, which from the equation, 1 mole of HNO2 gives you 1 mole of sodium hydroxide. Again, stoichiometry. That means that we would need 0.01 moles of sodium hydroxide. We then have the molarity of sodium hydroxide, so we could technically divide by the molarity, which would be 0.1 moles per liter of sodium hydroxide. The moles will cancel, leaves us with liters, and we would get 0.1 liters or 100 milliliters of sodium hydroxide would technically be needed to get to the equivalence point and use up all of our nitrous acid. That is kind of the long way to truly figure it out. Because this is a 1-to-1 relationship between the acid and the base, you could also figure it out with sort of the dilution equation, M1V1 equals M2V2, where we would be solving for V2, which would be M1V1 divided by M2. And that would get you, for our M1, 0.1 molar, our V1, which is 100 milliliters, divided by our, get this out of my way here, divided by our M2, which is also 0.1 molar. These guys cancel, and you're left with 100 milliliters of sodium hydroxide that's needed. Again, same answer. That's the short version of how you do the long stoichiometry part. So, I mean, there's a couple different ways you can do it. Just so we're clear, though, if you are going to use this one, which sometimes people will call the titration equation, it only works correctly for a multiple relationship of 1-to-1. So if your acid and base does not have a 1-to-1 relationship, you do need to take that into account. Otherwise, you will get the wrong volume. So those are two sort of ways you can figure out the volume to reach the equivalence point. There's actually a third way, which I'll show you right now. And let's go to the actual sort of problem here. We're going to take our HNO2 plus our sodium hydroxide. Again, going to give us some water and some sodium nitrate. So we want to do this table in moles. So we're going to take our moles of our nitrous acid, which is 0.1 liters, converting the milliliters into liters, times 0.1 gives us 0.01 moles. Now, if for some reason you couldn't figure out the volume to get to the equivalence point from the two calculations above, one thing that you should know based on our conversation is if we are at the equivalence point, the moles of my nitrous acid in this case should also equal the moles of my sodium hydroxide. So really, without doing a calculation or knowing the volume, because you are at the equivalence point, you actually should know that this number here would be the same as this number here, because that's basically what the equivalence point means. So if you happen to sort of work at it this way, sort of the third way you can figure out the volume, you would know that the moles of the sodium hydroxide should be 0.01. And that would lead you right to this part of the calculation, that if you have 0.01 moles of sodium hydroxide divided by the molarity would get you to the volume. So even if you couldn't figure out the first part of it, you could figure out this part. You then could do this calculation or that part of the calculation, and you could figure out basically the volume that you would need to reach the equivalence point. So there's really, kind of a few different ways you could get to the volume to reach the equivalence point. Hopefully you know how to do one of those ways. So since we are here at the equivalence point, our change, we can't really mess up since we only really have a choice of one number. Guess you can mess up if you write the wrong number there. Here again, I'm ignoring water as it will not have any effect. That means that we have 0 here, 0 here, 0.01 moles here. Why it's important to figure out the volume to reach the equivalence point is for right here. We need to convert this back to molarity at this point. So we do need to know what the total volume is. Again, we started with 100 milliliters of our nitrous acid. And through however calculation you want to do there, you figured out you needed also 100 milliliters of the sodium hydroxide. By the way, as well, even shorter way to figure it out is if the acid and base have the same concentration and they're a 1-to-1 relationship, you need the same volume to reach the equivalence point. And in this case, we needed 100 milliliters to reach the equivalence point. That means our total volume is 200 milliliters, or 0.2 liters. So we would divide this guy by 0.2 liters, which is our total volume. And we would end up with 0.05 molar. of our sodium nitrite, which is left over. Any questions on that so far? So when we look at the ice table, we see that the only thing we have left is a salt. And if we also know where we are in this titration and the type of titration, we should know that this salt should go through hydrolysis. Not only should it go through hydrolysis, we should know that this salt should go through hydrolysis and it should produce hydroxide and be basic. So again, if you understand the different parts of the titration curve, if you understand what you should expect to see, it will help you tremendously as you go through the calculation because you actually know what it should be before you do the calculation. So knowing that it should go through hydrolysis and knowing that it should be basic, we should know that this salt will break apart into sodium ion and the nitrite ion. Knowing that sodium is group 1 will not go through hydrolysis, but this one obviously came from our weak acid here, which means it is going to go through hydrolysis. So this is the part of the titration where we talked about you need not just one table, but you do need 2 tables here. Since it came from an acid, it's going to act as a base, and that means it's going to accept the H+. Also, logic tells us it doesn't have an H+ to give, so it's got to accept, and we will get HNO2 plus some hydroxide. And also, as we talked about, without doing a calculation, that should automatically scream to you, this is going to be basic at the equivalence point. Our initial concentration here will come from our previous equilibrium step, and that would give us 0.05 molar. And again, you do want molarity here. These are going to be zeros. Change will be minus X plus X plus X, which means when we reach equilibrium, 0.05 minus X, X, and X. Any questions on the second table that's going on here? Now this is going to go into our K expression, which in this case would be our products, which would be X squared over our reactants, which is 0.05 minus X. And since we know this is basic, since we see OH minus, this is actually going to be a KB value. Again, very common in this. You are not given the KB value, but you're given the KA value. So that is where the KW equals KA times KB. And the KB would equal 1 times 10 to the minus 14, which is our KW value, divided by 4.5 times 10 to the minus 4, which is our Ka value that was given to us in the problem. Gets us 2.22 to the minus 11. And again, also where people screw up the most, they decide I'm just going to use the Ka value here instead of the Kb. So again, really important to conceptually understand what's sort of happening at this point in the titration so that you don't really screw up your calculation. We're going to assume X is equal to 0. That's going to give us X squared over 0.05 equals 2.22 times 10 to the minus 11. We're going to multiply the bottom to the other side and also take the square root. And if I do that, we get an answer of X is equal to 1.05 times 10 to the minus 6. We do want to check it, so we're going to divide it by 0.05. We're going to times it by 100, and you're like 0.002%. So just to save some space, to check is good, yeah. That means when we go to our table, X in this case is equal to the OH minus concentration. So that means that the OH minus concentration equals X, which is 1.05 times 10 to the minus 6. Again, that does not give you the pH, though. It gives you the pOH, which would be minus the log 1.05 times 10 to the minus 6. And that gets us a pOH of 5.98. Also, if for some reason you thought that that was the pH value, that definitely should not make sense to you, because 5.98 is acidic, and you should know that the pH should be basic. Let me just grab your question there. Yeah, the KW is the constant, the same one that we used earlier on in the chapter. Is the 1 times 10 to the minus 14. So you always have that number, that 1 times 10 to the minus 14, which is KW. It's always a constant unless the temperature change, but most of the time it will be 1 times 10 to the minus 14. All right, so we know that that's definitely not the pH because would be acidic. So the pH would equal 14 minus our pOH, and that is going to give us a basic pH like we would expect of 8.02 in this case, which again, if you understand conceptually that at this point in the titration, you should hit a basic number, that is a good way to check yourself as well. So again, extremely important in these problems. As you can see, there's a lot of calculations going on to really have that sort of understanding before you start it, because that will help you not get so lost sometimes. People sometimes just jump right into these calculations without thinking about sort of what's going on, and they get halfway through and get kind of lost. So it's good to have sort of a plan before you jump in. And if you understand sort of the different parts of the titration curve like we talked about, it should really help focus you on sort of the right path. Any questions over any of those numbers came from or anything like that on this particular one? Okay, so that takes us to, I think, the last part of it. I'm just going to go back and double check. I think it's 105, if I'm not mistaken. Yep. So for part D, doing the same titration, we're going to figure out what the pH is once we add 105 milliliters of the base. So let's see, I think I got one more page. Yep. Okay. So let's just get all of our stuff set up here. So we're in part D now. And in part D, we have added 105 milliliters of our 0.1 molar sodium hydroxide to our 100 milliliters of our 0.1 molar nitrous acid. And again, same Ka value that we've been using. All right, so same deal here. We are going to have our equation. And just like normal, we do want to do this in moles because we are adding volume, obviously. So we're going to take, for our nitrous acid, the same amount, 0.1 times 0.1. Again, the 0.1 would have converted our milliliters into liters, divided by 1,000, or move the decimal place 3 places to the left. Gets us 0.01 moles. Our sodium hydroxide here, we have 0.105, which is converting into liters, times 0.1, 0.0105 moles. And 0 here. Now, if we weren't in a problem where we were doing multiple steps, we obviously know that we are past the equivalence point. We should, right? Because we just did the equivalence point, obviously at 100 milliliters. So we're past the equivalence point here. But if this was sort of a standalone problem, if you will, again, you can use your ice table and your moles to figure out where you are in the titration. And here we see that we have more moles of what we're adding than moles of what we started with. So again, whenever you have that situation, you are past the equivalence point. So again, if it was just sort of a standalone problem, you could figure out that you're past the equivalence point. That also should tell you that when you're past the equivalence point, like we talked about, there's a switch that occurs, and now our limiting reagent is the acid, and our excess reagent would be the base. I mean, here's the point where you pretty much ignored the indicator and you just kept adding because, hey, you had more in your burette. Why not just keep adding the sodium hydroxide? So the change part here is different than before because we're past the equivalence point. Again, we can't have a negative number, which is just the logical way of thinking about it. So you always want to use the smaller number here. But it's going to be our nitrous acid, which is going to be our limiting reagent. So 0.01 moles across is our change. That is going to get rid of our nitrous acid because we're past the equivalence point. That is going to leave us some moles of our sodium hydroxide, which would get us 0.0005 moles. And if I don't hit that button there, 0.01 moles. Again, at this point, our total volume going to be 100 milliliters we started with. We added 105 milliliters of our base. That is 205 milliliters, our 0.205 liters. So like we talked about before, after that first table, I would get in the habit of converting it back to molarity so you don't mess up any further calculations that might need to be done. So we'll get that 0.005 divided by 0.205 gives us 0.00244 molar. And for our other guy here, 0.0488 molar. If we look at our ice table, we have sodium nitrite, we have sodium hydroxide related there. These two guys are not related. Yes, not related. So again here, what people always screw up on is they decide I'm just going to use the Henderson-Hasselbalch because again, I got two numbers. Why not really? The why not is it would be wrong in this case. Again, sodium hydroxide cannot be part of a buffer. And sodium nitrate, they're not even related to each other in that sense. So like we saw at the equivalence point, this guy here will go through hydrolysis. But again, it will act as a base. But like we talked about earlier, we have this strong base that is there. And out of the two, we will ignore the contribution here from our conjugate base. And the major contributor for our hydroxide would be the strong base. So that means that the hydroxide concentration, not the H plus concentration, because it's a strong base, would be 0.00244. And that means that the pOH would be minus the log of that. And if we do that minus the log of 0.00244, we get a pOH of 261. And again, if for some reason you thought that that was the pH, it should not make sense to you because clearly at this point, we're just dumping strong base in there. We're adding a lot of hydroxide very quickly. And that's why we see that jump in pH usually after the equivalence point. So to get to our pH, we do need to subtract the 14. And if we do that, looks like it's 1139, which definitely is basic here. And what we would expect. You could also see a pretty good jump from our 100 milliliters at 8.0 pH to about 5 milliliters more we go up to 11.39, so almost 3 pH units by adding 5 milliliters, which, you know, is a good amount, but not a tremendous amount. So that is definitely sort of the part of the curve, as we saw, where we're at that equivalence point, and now we have jumped and starting to come, you know, back the other way in terms of our pH. Question on that calculation: are titration calculations anywhere along the way? And again, extremely important, like I said, to conceptually understand each of those titration curves we went through, each of the parts of the curves. And like I said, even before you pick up the pen, the paper, whatever it may be, to do the calculation, you should have in your head what is going on at that point in the titration. And you actually should know what calculations you should be doing before you even start them. And that obviously makes it extremely easier than, again, what a lot of people do, just kind of blindly jump in without really thinking about what's going on. And very often people get lost or do the wrong calculation. Any questions on titrations, titration calculations? Obviously, you will need to know those three sort of curves. You'll also need to know how to calculate the pH anywhere along those curves that I give you. Maybe we'll just have one test where you have 122 points on a titration curve to calculate. I'm kidding, by the way. Do not send me emails. But you do need to be able to calculate, obviously, the pH in any of these types of calculations. So we talked about strong acid, strong base. We talked about weak acid, strong base. And here on the end, we talked about a strong acid, weak base titration. You need to know the curves, what they look like, and again, how to do the calculations. Any questions on any of that? Sure, that was this one, yeah. Any other questions on these? Okay, so what we're going to do is we're just going to finish up the chapter. We're actually just going to talk a little bit about indicators. I think it's only a couple of slides and sort of the selection of the indicators, and then we'll officially sort of be done with that. So in terms of the equivalence point, yeah, and that's also a very good sort of question. In terms of the equivalence point, it does depend on the type of titration that you're doing as to what you would expect the pH to sort of be. Now, the very first one that we talked about was a strong acid and strong base titration. And when you do a strong acid with a strong base in a titration, you would expect the pH to always be 7 at the equivalence point. And that is because in that titration, the only thing that you are left with in terms of what is there once you reach the equivalence point and exactly at the equivalence point, the only thing that you're left with is a salt that is a neutral salt. So if you look back on our notes, what we had in that very first one, it was sodium chloride. And sodium chloride is a neutral salt. It contains sodium ions, which is group 1, which is neutral. And it contains chloride, which came from HCl, which is also neutral. So in a titration where you have a strong acid and a strong base, 100% of the time at exactly the equivalence point, the pH should be 7. Now that is different than a titration like this example that we did here and the second titration curve that we talked about. In a titration like this one here that's on the screen and the one that we talked about on the kind of graph, when you do a titration of a weak acid with a strong base, so you're adding again the base from the burette to the acid, when you reach the equivalence point and exactly at the equivalence point in that type of titration, you will also be left with a salt like we were here. Now, the difference between the salt that you're left with here and the salt that you're left with in the strong acid, strong base titration is that this salt in this type of titration will go through hydrolysis. And it is the part of the salt that came from the weak acid. So because this titration has a weak acid involved, we are going to generate a conjugate base, and that conjugate base will be relatively strong. Remember, it's an opposite relationship. So if it comes from a weak acid, it's going to be relatively strong. And what that means is it will go through hydrolysis, which is why in this type of titration, at the equivalence point, we actually have to do some calculations because we have to do that second ice table, which is the hydrolysis reaction. But in this type of titration, you will always produce a salt that will react with water. And when it reacts with water, that salt will always produce hydroxide, which means we would expect in this type of titration, regardless of sort of what combination of weak acid, strong base you put together, we would always expect that salt to continue on and produce hydroxide, which means in this titration, we would not expect the pH to be 7 at equilibrium. At the equivalence point, we would expect the pH to be basic. So we actually would expect it to be above 7 at the equivalence point. This happens to be 8.02. It could have been like 8.3. It could have been 9 at the equivalence point, but it definitely should be basic in this type of titration. And then in the third type of titration, which was that one that went, where are we at there? This type of titration where we take a strong acid and a weak base, when you reach that equivalence point here, you again will be left with a salt as the only thing that's left over at that point. So all three of these titrations, once you reach the equivalence point, you technically are left with just a salt. But the difference here is the salt that you would be left with, in the example that we did when we went through it, I think was ammonium chloride. And when we look at this salt at the equivalence point, the chloride, which comes from HCl, will not go through hydrolysis because it's a neutral salt. But this ammonium, in this case, came from NH3, which is a weak base, which means this is a conjugate acid. And it will go through that reaction we saw where it's going to act as an acid and donate the H plus over, which means in this type of titration, no matter what combination of strong acid, weak base you put together, when you hit the equivalence point, you will always have a salt that forms, and that salt will always generate H3O plus, which means we would expect at the equivalence point in this type of titration for it to be acidic below 7. So technically speaking, 7 is only at the equivalence point in our strong acid, strong base titration, which is somewhere, one more, which would be this titration here. So pH of 7 only for this type of titration at the equivalence point. pH above 7 in this type of titration, which is our weak acid, strong base. And equivalence point for that last one we were just talking about below 7 because, again, of the salt that's being generated. So for all of them at the equivalence point, moles of acid and moles of base equal each other. It's really the salt that's generated which will determine whether it be acidic, basic, or neutral. So just by knowing the combination of acid and base you're putting together, is it a strong and strong? Is it a weak and strong? You should know before, again, you even do the calculation at the equivalence point, would you expect it to be acidic, basic, or neutral? Any questions on that? And that's actually a very good sort of question for the last thing that we're going to talk about here in this chapter, which is indicators and how to sort of properly choose indicators. And let's get to that there. Oh, this is everything we just did on the other slides. Hopefully, there you go. let's get to that indicator. This will be in the recording, I suppose, as it scrolls by. In case you don't want to look at my scribble, you can look at these. All right, so let's talk about indicators and sort of how they work. So acid-base indicators, there's a bunch of different indicators basically that you could choose. Here's sort of a table of different acid-base indicators that you could choose. And really, indicators are sort of weak acids. There's a proteinized form like an acid, kind of like a weak acid, sort of the acid form of it. And there's also one where the H plus comes off, sort of a ionized version of it, kind of like the base version of it. And depending on the ratio of sort of the acid version to the base version will give you sort of a different color. So if technically that ratio is of the acid part with the H on it is greater than or equal to sort of 10, the color that we typically will see is the acidic color. While if that ratio is less than 10, we typically will see the base color. So here's some different ones. Let's talk a little bit about phenolphthalein, maybe, if I can find my thing here. So down here is phenolphthalein, and it actually starts right around here, if you can kind of see it. It's actually in this range-ish right there. And at about 8.3 to about 10-ish or so is the pH range. 8.3 to about 10 is sort of the pH range at with phenolphthalein works. So as we talked about, closer to that 8 is kind of colorless. And then as you can see, you get that gradual pink color sort of coming in as you get closer to that pH of 10. Again, it gets darker in terms of that pink color, although I'm using green right here. It will get that darker pink. And when we use something like phenolphthalein, we want it to change color around the equivalence point of our titration. And around the equivalence point, usually again of titrations, if you use this for something like vinegar and sodium hydroxide, which maybe you've done before, vinegar, right? And sodium hydroxide, vinegar really is acetic acid. And acetic acid is a weak acid. Sodium hydroxide is a strong base. So as was sort of the earlier question and what we just were talking about, without doing any calculation, when you have a combination of a weak acid and a strong base, when we hit that equivalence point, which is typically where we want to use an indicator, we know it should be basic, which is why we do use oftentimes phenolphthalein, because the equivalence point in that titration is 8 and change. And that's also why they tell you, again, as we talked about, that you want the lightest color of pink that you could get, because the lightest color of pink that you can get would put you in this range. And that means that you would probably be very close to the equivalence point. If you went kind of the super dark color in pink, my favorite, potentially that could put you way at the other end of the spectrum here. And that would mean obviously you'd be more at a pH of like 10-ish. And that could mean that you potentially have way past the equivalence point or gone way past the equivalence point. Now, as we talked about earlier, because as you approach the equivalence point, it technically goes vertical. Technically speaking, you could jump the pH a lot by adding a very small amount. And that's why I was saying that if you're doing a titration and you're very sort of careful as you're doing the titration and you're adding maybe only a drop at a time, maybe you don't wash down the drop with some water or anything like that and dilute it, but you're just adding a full drop at a time as you get close to the equivalence point. Even if you did see a pretty big jump in color and you're doing that adding basically, one drop at a time, you probably, even though you probably jump way high up on the list in terms of where the pH is, volume wise, you're probably still pretty close to the equivalence point because it does go vertical there. And as we talked about, you don't have to add a lot of volume to move the pH a lot. The reason they tell you to kind of go slow and try to get the lightest color of pink as you should, again, that should put you closest to the equivalence point. But in terms of volume, as long as you're not like streaming it, like just adding a straight stream of, say, sodium hydroxide into your beer from your burette into your beaker, if you kind of were doing drop by drop, even if you sort of went too dark in color, the volume would still be this probably about the same, and you still would be okay in terms of your calculations. But again, if you're streaming it in there like a big steady stream of sodium hydroxide and you just blow right past the equivalence point, you really could find yourself volume wise way away in terms of where you should be. So the idea when we pick sort of a indicator to use for titration, the real thing that you want to look at obviously is, do you get a color change near the equivalence point? So we do want a color change to occur near the equivalence point because an indicator really is a visual reference for us to know to stop the titration. So if your equivalence point is right in the darkest part of it, and there really is no color change that's happening, that's going to be a really bad indicator. So for example, if we look at crystal violet, which is up here at the top, we'll just take this guy, which is at top, kind of a yellowish color. Down here at 0 pH, kind of a bluish color at a higher pH. So for example, if our equivalence point was a pH of, let's just say 2 or maybe 3, this would not be a great indicator to choose because by the time we get to our equivalence point, which is over here, this has already been blue for a long time, right? So it's been blue for a good period of time, which is way before our equivalence point, right? So it would have changed color before our equivalence point. Also, that would be a terrible choice for the acetic acid and sodium hydroxide titration because our equivalence point is way over here in the basic range, which also means that that indicator is going to change color as soon as you hit like a pH of 1. It's going to start to change color and will remain that color for the rest of the titration. So a lot of these here on this list have, you can see a distinct color change, which is what you're looking for when you're picking an indicator. You obviously want that color change to occur as close to your equivalence point as you could get so that you have a visual reference as to when to stop your titrations. And knowing what you expect in terms of the equivalence point pH is really important in picking the proper indicator. If I was to have a titration where the pH would be 7 at the equivalence point, right? That would be here. I'll try to draw a straight line, but maybe not the best straight line. But you would want to pick one of these indicators where you would maybe see a color change occur near 7, which my bad straight line maybe would put us over here at this bromothiamol blue. You get probably a change from kind of a greenish color to more of a dark blue color, or like a yellowish to a greenish. Would probably tell you you're nearing the equivalence point. Technically speaking, this would not be good, right? Because it wouldn't start to change color until about here, which is way past your equivalence point. So you want to choose one where you see a noticeable color change near that equivalence point to give you that indication you should stop, and understanding where the equivalence point should be for all these different types of titrations that we do will allow you to figure out, which one would be a good indicator or which one would be a bad indicator. So why don't you take a moment here and think about this titration here. And here's a list of some indicators, and choose the indicator or indicators that would be good for perhaps this type of titration. So just take a minute or two and think about which ones would be good. All right, so looking at this one, we want to think about what these things are. So we just saw HNO2 in that last problem. We do know that's a weak acid. KOH, we do know is a strong base. And again here, when we take a weak acid and strong base, titration curve looks badly like that. We know that when we reach the equivalence point, it should be basic, like we did before in that calculation, which pretty much means since these guys here work off of a pH range, since it's more acidic, these would be not a good choice. Yeah. And again, the ones that probably would be a good choice would be perhaps these two here. Without having numbers or anything like that, we don't know specifically in that situation exactly the pH we would expect. If you did have numbers, you could do a calculation at the equivalence point and figure out pretty close to what you would expect to get for the pH. But these two here, which would be our cresol red and our phenolphthalein, that's how you spell it there, would be a good choice for that. The bromothymol blue, it might not be a good choice because it really only goes to 7.6, which is just slightly basic, but you got to think at that point at 7.6, it has already turned the blue color, and you wouldn't be able to see a distinctive color change occur again, which is why that guy would not probably be a good choice, at least with the cresol red. You have a good little range into that reddish color where it would change. So it would start at yellow at 7.2 and then kind of go reddish at 8.8-ish range, or probably before that. So you'd be able to at least cover some of that basic range in terms of seeing the color change. And obviously phenolphthalein, which we're familiar with, more colorless at 8.3, getting to that pinkish color towards the 10. And again, you'll be able, that covers a pretty good range of basic equivalence points for you to kind of see the color change. Any questions on how to pick a right indicator or anything for that in terms of the titration that you'll do? Again, the take-home message is these work over a pH range. They do change color depending if it's sort of acidic or basic within that range. And we would want to have one where it changes color near the equivalence point would be the proper way to choose that. Any questions on that? Okay, that actually does conclude, I believe, this chapter in terms of lectures. So we will stop here for the lecturing part of lectures. And we're going to talk about sort of the next experiment here, which is buffers, just get everybody on the same page on that. And then we will call it a day here, I think. All right, I'm just going to stop sharing for just a second. And we want, let me do that real quick. Just give me 1 second to get something up here to write with. Okay. Okay. Okay, and find the right thing here to go. Click that. Click that. And click that. All right. Okay, so what we're going to talk about now, maybe. Is Try to find the right one to click on here. Hopefully that. All right. Do our best here with technology. All right. All right. So, and the next one, which again, this lab is not up yet. As soon as we're done here, I will probably make it available, obviously, if you want to start working on that. Obviously, before we start talk about this one, you do have that pH and hydrolysis one again due at the end of the week. So hopefully you're going through that one. A reminder again, the lab report for that is pretty much all the pages they have you submit. So you do all that work and make sure you submit all the sort of assignments and stuff that you need to do and run through the simulation. So for the buffer lab, it's going to be a lab where you're going to be making a buffer, and you're going to be making a buffer at a specific pH and also a specific molarity. So obviously we're talking about buffers, which will involve our Henderson-Hasselbalch equation. And we talked extensively about buffers, how they work, and what they're made up of. Remember that a buffer is made up of a weak acid and its conjugate base, or the salt of its conjugate base. Or it could be made up of a weak base and the salt of its conjugate acid. Remember that a buffer itself cannot be made up of a strong acid or strong base, so it cannot be directly made up of that, the buffer itself. But you can make one from a strong acid or strong base, which we will also deal with in this experiment. So you will be assigned a a target pH to make your buffer and a target molarity to make your buffer. And there's a couple of methods, but the first method, as a sort of outline in the lab, if you read it, is, I think they call it method 1, if I'm not mistaken. But for example, in method 1, we can use the Henderson-Hasselbalch equation to figure out a couple of things, including how to actually make the buffer. The first thing that we want to think about is, as we talked about, if we keep the concentration of the base equal to the concentration of the acid part in the buffer, that usually will give you the log of 1 here. And that means that in terms of selecting a good weak acid or weak base to make a buffer from, you do want to choose one that is sort of plus or minus 1 of the pKa value. So plus or minus 1 of the pKa value is a good choice in making a buffer. So again, if you want to make a buffer of 4.60 pH, you may choose something like acetic acid, which has a pKa value of 4.74. That would be a very good choice. A bad choice might be something like ammonia, which has a pKa value of like 9.25, give or take. I could be wrong on that number, but it's something like that. And that obviously would be a terrible choice probably to make that buffer at a pH of 4. Again, it's nowhere really near it. It would take a tremendous amount of adjustment and probably won't work very well, that buffer. So the first part of what you'll be doing is trying to figure out what combination of weak acid or weak base should I choose to make my buffer from. And you will find a list of choices in the lab. So you'll have a list of choices, and from those choices, you need to choose the one that is really closest in terms of pKa values to the pH that you're trying to make in terms of your buffer. This obviously will require you, trying to remember off the top of my head, I don't know if the pKa values are given to you in the lab. I don't think they are. So again, you may have to reference some tables, book or something like that, some type of source to sort of find the pKa values for all your choices. And then obviously you would want to choose one, like in this example here, which hopefully is not a real example. You would want to choose, obviously, to make it out of acetic acid. If I were to make my buffer out of acetic acid, that would be my weak acid part, which means, again, in order for it to be a buffer, I would also need a conjugate base part, which in this case should be acetate, which most likely would be found in the form of not just acetate, but something like sodium acetate. So again, on that list, you may find the other part that goes with it. Actually, I think they may actually be right next to each other on the list, but you would want to find, obviously, its partner. Okay. And this is the first part of what you'll be doing, is trying to select the correct components to make the buffer that you need to make at that selected pH. Once you make that selection in terms of what I'm going to make my buffer out of, you then will need to figure out how to make it. And what that means is some of the reagents that you could choose from could be solids. Some could be solutions or liquids, which means if it's a solid, you need to figure out probably how many grams to weigh out. If it's a liquid, you need to figure out probably how many milliliters are needed. So again, the first part here is going to be, you need to select what would be a good weak acid or weak base to make my buffer out, along with its conjugate partner. Then you need to do some calculations, which we'll talk about in just a second here, as to figure out physically, if you were going to make this buffer, how much you need to weigh out if it's a solid, how much to sort of measure out if it's a liquid. I almost think most of them, because you're going to be using a simulation program, may be liquids, but some may be solids as well. So you do need to sort of figure out both of those. Any questions on that so far before we sort of talk about the calculation part of how to figure some of these stuff out? Okay, so let us talk about, and again, if you do have questions, feel free to ask them. Just flip the page here. Now, let's say, for example, you wanted to make a pH. I think I'll try to use the one that's in the example in the lab. Let's say your desired pH was a buffer that had a pH of 5. Okay. And let's say that when you sort of scoured the list of weak acids or weak bases to choose from, the closest pKa that you could find, we'll say it was 4.5. Okay. So you decide, I'm going to choose this as the pKa for whatever acid that may be for. Now, you could use the Henderson-Hasselbalch equation to figure out how much base and acid that you need. Again, if we look at the pH is equal to the pKa value plus the log of the base over the acid. And remember earlier when I said you could take the base over the acid, and you don't necessarily have to, in the Henderson-Hasselbalch equation, have these guys in molarity, but these could technically be the moles of each of that. So that would be the moles of your base on top and the moles of your acid on the bottom. You could put these numbers into your Henderson-Hasselbalch equation, and basically you would get 5 is equal to 4.5 plus the log of the base over the acid. And if we subtract the 4.5 to the other side, we get 0.5 equals the log of the base over the acid. If I don't hit the button there. To get rid of this, we're going to take the 10 of both sides, right? So the inverse log of both sides. And if we inverse log 0.5, we get something like 3.16 equals the base over the acid. And in this particular case, that would tell us that for every mole of base that we need 3.16 moles of our acid, right? By multiplying the A to the other side. Any questions on that? Now, knowing sort of our ratio of what we should have is important. So basically, we have 3.16 moles of acid for every mole of base that we have going on there. And the other thing that's really important when you make a buffer is the molarity of the buffer. And the molarity of the buffer is important, and also the volume of the buffer. So again, I'm just gonna, I think, pick the numbers that are in the lab introduction. I think, let's say we wanted to make our buffer a 1 molar buffer, and we wanted to make 1 liter of a 1 molar buffer. Within a 1 molar buffer and a 1 liter of it, if we multiply that together, we will enter with 1 moles total. So in our buffer, we will have basically 1 mole total of moles flying around. And remember, in our buffer, there is moles of our acid moving around, and there's moles of our base. So 1.0 moles total is the moles of our acid plus the moles of our base, right? And when we add it together, again, it should equal moles. And that means that if we take our ratio, which we sort of figured out over here, that the moles of the base equals 3.16 moles of the acid. And if we substitute that in to here, that would give us that the 1 total moles, 1 mole of all of the moles, would be the moles of acid plus 3.16 moles of acid, which should technically give us 4.16 moles of acid when we add it together. This is 1 plus 3.16 equals 1 mole total. We divide both sides by 4.16. That would tell us that the moles of acid in this made up buffer should be 0.24 moles. Any question on that part of the calculation? And basically what that 0.24 moles represents is the moles of acid we need to put in there. We already know that the moles of the base, which is up here, is equal to 3.16 times the moles of the acid. So to find the moles of the base part of the buffer that we need, we would take 3.16 times the moles of our acid, which is above. And that would tell us that to make this buffer and have the right amount of moles of our base, we need to put 0.760 moles in. Of our base. So if we were going to make this buffer that has a pH of 5 and a molarity of 1 molar, and we want to make a grand total of 1 liters of it, we would need to take off of the shelf 0.24 moles of the acid part. We would also need to take off of the shelf 0.76 moles of the base part of the buffer, and we would need to mix them together with enough water to get us a total volume of 1 liter. We could also check our calculation if we take this number here and we take this number here. It obviously should add up to our 1 mole of total moles, right? Which it does. So that equals 1 mole, which is our total moles we should have in that mixture. Any questions on that part of the calculation? So again, this is sort of an example calculation of if we wanted to make a 1 liter buffer that has a molarity of 1 molar and a pH of 5. This is essentially how many moles of each of those that we would need. So why is that important to figure out the moles of the acid part or the base part? So for example, let's say our acid in this example was a solid and it had a molar mass of 30 grams per mole. Again, I'm just making this up, okay? And let's say that our base part of this buffer was a liquid that had a molarity of 0.5 molar. We could use each of these information here to actually figure out if we were physically going to do it, how much of each of those things we would need. So for example, for the acid, since it's grams, we could take the moles that we calculated of what we need for the acid. We could take the molar mass that you could get from the periodic table if it's not given to you and multiply it by the molar mass. The moles would cancel, and in this made-up example, we would have to go weigh out 7.2 grams of our acid. And if we wanted to figure out our base though is a liquid or a solution. This is a better way of putting that. And it has a molarity, but we could still use the moles we calculated. And we could use the molarity. And we would want to divide by the molarity. The moles would cancel. And that would give us 1.52 liters that we would technically have to measure out for our base. Or again, that would be something like 1,520 milliliters in this really bad made-up example, right? 1,520 milliliters of our base. And these would give you actual numbers that you could physically go and weigh out. And if you were to make this buffer, in this made-up example here, you would go to the balance, you would weigh out 7.2 grams of your acid. So say it was acetic acid, you would weigh that out if it was grams. You then would take 1,520 milliliters of the base, and you would then put the acid into the base, mix it, get it to dissolve, and the rest would be water, right? Up to 1 liter in this case. Any questions on that there? All right. So this is sort of the calculation that you would do here in this case, and and you need to do this calculation to figure out again really the moles part here of each of these guys, and then you can basically figure out the mass if it's a solid that you need to make it, the volume of the liquid that you need to sort of measure out if you're going to sort of use a solution to make it, and then you're going to have to write a procedure, if I'm not mistaken, how you're going to physically make that lab. So you'll have to write the procedure of what equipment you're going to use to make it, how many grams you're going to use, obviously, to make it. If it's grams, how much milliliters you're going to use to make it, to make up this buffer here. Any questions on that there? And that's the first part of the experiment. Then once you've sort of figured out your calculations, you figured out how you're going to make it, you got your procedure written out, there is, I think, a simulator where you will go and actually make that buffer that you're assigned, and you're going to verify the pH is what you expect it to be. And then I think part 2 of that sort of experiment is you're going to keep that buffer that you made sort of on the simulation or the simulator there, and you're going to basically test your buffer by adding acid or base to it and see if it resists changes in pH, which you would expect it to do. And you're also going to test in part B the water, which is not a buffer. So you're going to add basically acid and base to a water solution in the simulator and see what happens to the pH. Those you should expect to see a pretty good jump in pH, up or down, depending on what you're adding. And then you'll also add the same acid and base to your buffer, which hopefully, if you made your buffer correctly, it should obviously resist that change to the pH. Any questions on that there? Now, the last part of the buffer experiment, we'll switch that there, is one where we're going to make a buffer from only one part of it. And you'll need to choose what might be the correct other part to make the buffer from. So for example, let's just say that my acid that I choose is acetic acid, which is a weak acid. And let's just say that I want to make an acetic acid and a sodium acetate buffer. Again, you want to make this at a target pH, just like before. And it's going to be the same pH target that you will be assigned for the first part. The difference is we're going to make it by reacting, in this case, acetic acid with a strong base. So let's say I put sodium hydroxide in with it. It is going to react and produce sodium acetate and water. Now, when we make this, and again, I'm just going to make up numbers. So let's just hypothetically say we started with our 4 moles of this, 0 this guy, 0 this guy. We want to figure out how many moles that we need to add of our sodium hydroxide to actually generate a buffer. So just for example, let's just say we only added 1 mole of sodium hydroxide. And again, I'm just making this number up. Because technically, like we were talking about in the titrations, our sodium hydroxide in this case would be the limiting reagent. It is going to be the change that's going to occur. And what will happen is after that reaction is over, you'll be left with 3 moles of your acetic acid, none of your sodium hydroxide, 1 mole of your sodium acetate, which obviously, you could convert into molarity. Not necessarily important at this point. But the idea here is we started with only acetic acid. We reacted it with sodium hydroxide to actually produce sodium acetate. And these are really the only 2 things that are left over. And this is why this is still a buffer, because all of our strong base is gone. And what we are left with is a buffer that we made. So the goal of the sort of last part of the experiment, which I think is part 3, if I'm not mistaken, is for you to make basically the same buffer that you made in part 1 with the same pH and the same molarity, but you're going to make it through this process of either adding a strong base like we did here. You could add a strong acid And that could generate a buffer when you take, kind of like the titration curve we did, the last one where we took HCl plus some ammonia will give you NH4 plus and Cl minus. This is a weak base and is conjugate acid. And this also would generate a buffer. If we did kind of the same thing, if we started, say, with 1 mole of this guy, 4 moles of this guy, 0 of this guy, change here would be 1 mole, plus 1 mole, which means at equilibrium 0, 3 moles, and 1 mole left over of this guy. So this would be a way where you could generate a basic buffer by reacting a weak base with a strong acid. Or in the top example, you could generate an acidic buffer where we react a weak acid with a strong base. So part 3 of the experiment, again, you're going to be making the same buffer as part 1, but the way you're going to do it, I think they call it method 2 in the experiment, if I'm not mistaken. And you can read all about this again in the introduction. They sort of lay it out there as well. Through method 2, where we do a reaction. And again, this is still a buffer in the bottom because all of our strong acid is gone. So what we are left with is basically a buffer that has been made in situ, which is basically in the reaction. So you basically make a buffer as part of the reaction, which is essentially what happens when you do a titration, like we saw in those titration curves before the equivalence points. You can make a buffer, and that's essentially what you would have. And at that point, you would have a buffer, which you can then obviously treat with either acid or base and see how it resists to pH. The other part of this is, by the way, in order to do this, you still need to use, and I'll let you kind of work through those calculations, you still need to use the Henderson-Hasselbalch equation. You still want it at your targeted pH. So the goal here is to figure out the correct sort of ratio of these guys. And really what you're going to have to figure out is, I believe the sodium hydroxide and I believe the HCl, they are both solutions that have molarity. So really what you're going to have to calculate in order to do this correctly is to figure out the volume needed of each of these guys, or whichever one you choose. So you would need to figure out the volume needed of sodium hydroxide to add to your acetic acid to generate the right ratio of base to acid so that you end up with the correct pH. So when you get to part 3, you have to still think about your target pH. You have to think about the ratio that you need in terms of base to acid and sort of what is happening here. Ultimately, what you're trying to figure out is basically the volume of the sodium hydroxide you should add. Any questions on that? Now, also, I believe in part 3, if I'm not mistaken, I think it's the last part of the experiment. Once you sort of figure all this out, you then will have to figure out one last thing, I think, or 2 last things. You will have to figure out, once you have your buffer, how much HCl is needed to add to lower the pH by a certain unit. And also the second part would be how much sodium hydroxide would be needed to raise the pH by a certain unit. And it tells you in the experiment, you know, how much are you trying to raise the pH? How much are you trying to lower the pH by? So what that essentially means is, for example, in what we've been talking about here, our target pH was 5. So let's just say we wanted to lower the pH by 0.1 units. That means that our target pH would now become 4.9. And that would be what you would want to put into your Henderson-Hasselbalch for that part of the experiment, because you're no longer trying to make a buffer at 5. You want to make it at 4.9 to lower it down. So obviously we would add something like HCl to that to do that, and you would have to figure out how much HCl you need to add. So there's a few different things happening towards the end of the experiment where you're making the buffer sort of through a different method. And then secondly to that, you are going to be asked to figure out how much acid or base you need to add to your buffer to make the pH go up and make the pH go down. Any questions on all that? I know that's a lot going on in this experiment. Okay, so let's just talk about sort of the experiment and how we're going to sort of go through it. I'm going to make it available, I think, after we're done here today for this part. That will give you an opportunity to start working on it. I think, let me see here. Give me 1 second here. I'm just going to drop the screen off for just a second so I can take a look at something. So we could talk about what's sort of happening here. Okay. All right. So at this point, just looking at the schedule so everybody's on the same page. Today is the 28th. It is. Yes, it is. So officially, I'm going to open up the buffer experiment starting today. On Thursday of this week during lab, I'll be here for questions and stuff like that. By Thursday of this week, you should be done with the pH and hydrolysis experiment. So again, you could start focusing in on working on the properties of buffers on this Thursday. And we'll work into next Tuesday on it as well. So you could kind of be working through it. The exam, which is coming up, will be moved most likely to the 12th of May. So May 12th, and again, I'll put this on Blackboard as well, but not Blackboard, it's Canvas now these days. May 12th will be probably our next exam. That'll give us opportunity to finish the chapters we need. So we're going to work on the buffers lab all this week and maybe into Tuesday, and next Tuesday, which would be the 5th of May, we will transition from buffers and then start talking about the titration experiment, which we will get into at that point. So technically today, this Thursday, and then the following Tuesday, we'll kind of be working through this buffer lab. The buffer report will be pretty much what it says as you go through the module. There'll be turn this in for 10 points, turn this in for whatever, 30 points. So that will pretty much be the lab report for that, whatever it has you sort of turn in, download, fill in, and then turn in. That will be pretty much the lab report. So all just the parts. So it'll be probably very similar to the lab report for the hydrolysis one, where you had kind of all those little parts to turn in and stuff like that. So we'll work on it. You can start working on it today, or again, you should maybe finish up your pH and hydrolysis if you have not, since that's due at the end of the week. Thursday, you could kind of work on your buffer during lab. I'll be here if you have questions and stuff like that. And then next Tuesday, you could also continue to work on it. But by next Tuesday, we'll probably transition into also talking about the next experiment, which is titrations. And again, the exam will be most likely moved to Tuesday, May 12th. That should give us enough time to finish chapter 15. And we will continue to work on the titration experiment. Any questions on any of those things? Now, a couple other things about the buffers lab. You do need to be assigned a target pH and all that. So what I will do is try to think about how I want to do that. I will let you know how to get your assigned buffer when I post it and all that. So later on today, I'm going to try to figure out the best way to sort of do that, since everybody's not technically here right now. Has to individually send you something. So I may individually just kind of send you an email and say, hey, do number 1 for the buffer. And that means you'll see the table. The table is in one of the PDFs that you download for the experiment, and it'll have a table of all the buffer assignments with the pH and also the molarity on it. So I think I will somehow get you like what number you should do off of that table pretty soon here. So that will be the number that you should choose and kind of do on that. There's also parts where it says to sort of check your calculations and stuff like that with me. And again, I'm going to say that you should try to work on it probably by at least Thursday or into next Tuesday. When you get to that part, you can sort of check your calculations with me. If you feel good about your calculations and want to kind of get going with doing the simulation and all that kind of stuff, you can. But if you want to check your calculations, you can with me starting on Thursday. So starting on Thursday during lab time, or even after Thursday into next Tuesday, there would be opportunities again for you to check your sort of volumes and stuff that you calculated for part 1 and all that. But if you don't want to wait to get it checked and you feel good about your calculations, you obviously can run through the simulation. And obviously, if something's wrong, you'll just have to go back and do it again, I would imagine. Okay. So this buffers lab will be, I think, due towards the end of next week, as I think when it will be due. So again, if you finish up the pH and hydrolysis, you may want to kind of get going on this one as well. Any other questions on anything? Okay, so we will probably finish this up for today. And like I said, next few hours or so, a couple hours, or maybe even before that, the buffer labs will be up on Canvas if you want to kind of go through it and kind of look at it. And again, during lab on Thursday, I'll be here for any questions and stuff that you have on that lab and stuff. Other than that, thank you very much. We will see you on Thursday for lecture during our normal time. Have a good rest of your day.